In this lesson, we're going to take a look at alkyne alkylation with a brief introduction to organic synthesis. Terminal alkynes can undergo alkylation reactions. Alkylation is simply the introduction of a new alkyl group to an existing structure. Alkylation is important because it creates a new carbon-carbon bond, enabling the extension of a carbon chain. In the first example, 1-propyne is first treated with sodium amide, a strong base, followed by bromomethane, which serves as the alkylating agent. You can see that the overall reaction is the replacement of a hydrogen from the sp carbon of the terminal alkyne with the alkyl group that was attached to the halogen of the alkyl halide, in this case, a methyl group. The 3-carbon chain of the starting material was extended to a 4-carbon chain via the formation of a carbon-carbon bond. The second example is quite similar, starting off with 1-pentyne and alkylating with chloroethane to form 3-heptyne. If we look at the reaction mechanism, we can see that the first step is an acid-base reaction. A strong base removes the hydrogen from the sp carbon of the terminal alkyne, resulting in the formation of an acetylide ion. The negative charge of the acetylide ion is stabilized by the enhanced electronegativity caused by the sp hybridization of that carbon. The use of a very strong base like sodium amide makes this step thermodynamically feasible. In the second step, the acetylide ion acts as a nucleophile and attacks the electron-deficient carbon bonded to the halogen in the alkyl halide, displacing the halogen and forming the carbon-carbon bond. In general, both methyl and primary alkyl halides can be used as the alkylating agent in the alkylation. So now that we have access to our first carbon-carbon bond-forming reaction, we can take our first look at organic synthesis. Organic synthesis is the art and science of combining several reactions in tandem to prepare more complex and generally larger structures. So, example 1 shows a relatively simple organic synthesis problem. Here we need to transform ethyne into propane, and that transformation cannot be accomplished with simply one reaction. In a simple synthesis, a good basic strategy is to analyze the overall transformation with respect to the functional group changes that have occurred and the carbon skeleton changes that have occurred. So in this example, the functional group change is simply the transformation of an alkyne into an alkane, and that's a transformation we know how to accomplish. An alkyne can be transformed into an alkane by a simple hydrogenation. If we look at the carbon skeleton change, we can see that we're taking a 2-carbon skeleton and elongating it into a 3-carbon skeleton. We know that carbon skeletons can be elongated by alkyne alkylation. So fundamentally, we know that this synthesis will require at least 2 reactions. The order of those reactions is critical. If the hydrogenation were performed first, the result would be the formation of ethane, an alkane, and we'd still need to incorporate an additional carbon onto that chain. Alkanes are rather unreactive, and as of right now, we don't know any carbon-carbon bond-forming reactions of alkanes. But we do know a carbon-carbon bond-forming reaction of an alkyne, and that's the functionality we start with. And that means that the alkylation step has to be the first step. So we begin with the alkylation of this terminal alkyne using bromomethane as the alkylating agent, extending the carbon chain by 1. We're now left with transforming 1-propyne into propane, and that simply requires a hydrogenation using palladium on carbon as a catalyst. And that completes this rather simple 2-step synthesis. Example 2 is a little more challenging. Here, we're transforming ethyne into 2-butanol. The functional group change is the transformation of an alkyne into an alcohol, and that's not something we can do in a single step. When tackling synthesis questions, it's often useful to think of where things could have come from. In this case, an alcohol functionality could have come from the hydration of an alkene, and that alkene could have come from a Lindlar hydrogenation of an alkyne. So in this case, the functional group change is going to require at least 2 reactions. With respect to the carbon skeleton change, we can see that we're transforming a 2-carbon skeleton into a 4-carbon skeleton. In this case, that extension of the carbon chain by 2 carbons could be accomplished in 2 ways. We could perform a single alkylation, replacing one of the hydrogens on the alkyne with an ethyl group, but an alternative approach would be to replace both of those terminal hydrogens with methyl groups, extending the skeleton by 1 carbon on each end. Taking the first approach, we would transform ethyne into 1-butyne. We're then left with the functional group transformation of an alkyne into an alcohol. We need to set up that addition reaction by transforming the alkyne into an alkene using hydrogenation with Lindlar's catalyst. The resulting alkene then needs to be hydrated, and we can see that we need the alcohol to go on the more highly substituted carbon of that alkene. And that means we need a Markovnikov addition of water, So either the acid-catalyzed hydration or the oxymercuration reduction reaction will work. Note that in the second step, the hydrogenation with Lindlar's catalyst was necessary. The alternative, which would be to use the metal ammonia reduction to transform an alkyne into an alkene, is ineffective on terminal alkynes.